Today, we're starting a topic which is very important, probably the most important in elementary statistics course. Some call it the heart and soul of statistical analysis, and the topic is linear regression and correlation. Well, let's begin. We're gonna start with some definitions. The first definition says a correlation or association exists between two variables when one of them is related to the other in some way. In other words, if we were to graph the data points, they will be grouped around some curve. And the curves could be different. It could be a line. It could be a parabola, like you see in some of these slides shown on the screen. So right here, we observe a perfect parabolic correlation or association. In this slide on the right, we have not a perfect, but still a good linear correlation and or regression. And in the slide on the left, we see no obvious association or correlation. So the correlation is going to be measured by a correlation coefficient. We have the linear correlation coefficient that measures the strength of the linear relationship between paired X and Y variables. Those variables are quantitative variables. So we have a two-type, the correlation coefficient ranges in values from -1 to +1, with 0 representing no correlation whatsoever. -1 represents a perfect negative correlation, and +1 represents a perfect positive correlation. So the strength of the correlation is represented by not by the sign of the correlation coefficient but by its absolute value. The closer it is to either +1 or -1, the stronger the correlation. But if it gets close to 0, then there is no correlation. To further explain the positive and negative correlation, I'm going to give you these examples. For positive correlation, if a person can do a lot of push-ups, we expect him or her to also do a lot of pull-ups. This is a positive association or positive correlation. So the greater the variable X is, the greater the variable Y becomes. A negative correlation is the opposite. When the X variable becomes bigger, the Y variable becomes smaller. That's a negative correlation or negative association. For example, the more classes a student misses, the lower the grade on the final. So that would be an example of a negative correlation. So here's some examples of linear correlation. In the first slide, we have a positive linear correlation with a correlation coefficient R of 0.851. And then B is a better correlation it's also positive correlation. So how can you tell it's a positive correlation? Is because your values are increasing from left to right. That's a positive correlation. And on the last slide, on the top right, is a perfect positive correlation with correlation coefficient equal 1. So basically we have all our data values line up in the perfect line. That's when the correlation coefficient is 1. On the bottom row, we have negative correlation. So we could see that as the x value is increasing, the y value is decreasing, therefore the data group around a straight line that goes down. The slope of the line is negative. So the first slide, we have a correlation coefficient negative 0.702. And then the next one, negative 0.965. And the last one is negative 1. So observe that as the correlation coefficient approaches 1 or negative 1, the tighter the fit is, the better our data lines up. So the key concept of this section is to describe the relationship between two variables by finding a graph and the equation of the straight line that best represents the relationship. This straight line that we're gonna find, it's called a regression line. And because statistics is a new science, it has many different terms that represents the same thing. So regression line is also known as least squares line and the line of best fit or prediction line. All of these terms, they refer to a regression line. And just as a reminder, the equation of the line is y equals mx plus b. In stats, it's written slightly different. It's written b plus mx, where b is a y-intercept of the line and m is a slope of the line. Now, how we're gonna establish a correlation? Here's a flow chart, basically the steps that you need to take. Step number 1, you're gonna plot the data. You're gonna plot the data and you're gonna observe, is there a pattern to how the data fits? So for example, in this first slide that you saw, we have 3 different scatter plots from which we can get that in the first one represents no correlation. So the data points are scattered all around. Now in the second plot, we see that the data points line up, but it's not a straight line, it's a parabola. So this is a parabolic correlation, which we're not studying in this course. And in the third slide, we see that data group around the straight line. So that represents a linear correlation. So once we establish that there is a correlation, then the next step, a linear correlation, then the next step would be to find the best fitting line. In this course, we're gonna use technology to do that. The technology will find both the y-intercept and the slope for us. The equations look different in different books. For example, you may see b sub 0 and b sub 1 for the coefficients, or you could see a and b instead of b and m. So if you're using calculator, for example, TI 84 calculator will have this equation. A book that we study in the Triola book, for example, has this equation. So, but just keep in mind that they represent the same thing. They're talking about the straight line. And in order to describe that straight line, we need to find the y-intercept and the slope of the line. So next, we're going to find the correlation coefficient, which we're going to be discussing in more depth later. And then we're going to conduct a regression analysis, basically to figure out if this line is a good fit for our data. Can we use this line to predict some values? Because that's the goal. Why do we need this line? We need the line so we could predict some values. It's our model that we can use for future predictions. Now, if our line, the truth is that technology will give you a line no matter what. Even if there is no correlation, a technology will give you an equation of the line. So for example, if you look at this data set right here, we already mentioned that there is no correlation there. But if you put this data value into a software and ask it to find the best fit line, it's going to give you probably a horizontal line with a slope of 0. And that goes through the center of this group. But we understand that that line will not represent our data values. We cannot use it to predict data values at all. As a contrast right here, if we find this, the line that represents this set of points, then we could use that line to predict where our next data value will end up. So it's gonna end up somewhere around that line. So that is where the analysis of the correlation coefficient will come in. So here's some formulas that are used to find the slope of the line M, the y-intercept B, and the correlation coefficient R. I just wanted to show you the formula. I'm not gonna ask you to use the formula. As I mentioned before, we're gonna use technology, but these are the formulas behind the technology results. So let's take a look at our first example. It says the following data includes the year, make, model, and mileage in thousands of miles, and asking price in US dollars for each 13 Honda Odyssey. The data was collected from the website of the Seattle P1 on April 25th, 2005. So this is an older data set, which explains the prices. The prices are higher today. But anyway, so let's work with this data. And first of all, I just want you to mention, to turn your attention to the fact that we could make a couple of association here. For example, well, we're gonna find the age of the car, okay, of each car, subtracting the year it was made from 2005. That will give us an age, but we could associate either age with the mileage or age with the price. Age includes both of those variables, right? So what do they want us to do? Let's read question A. It says construct a scatter plot and compute a correlation between age and mileage for these minivans. So they want the association between the age and the mileage. And let's decide which one is going to be our X variable, which one is going to be our Y variable. Well, of course, X is independent variable and Y is dependent variable. And we realize the common sense tells us that mileage is dependent on age, and not the other way around. So age is going to be our X value and the mileage is going to be our Y value. And says, question B says, constructs a linear regression line. And we are going to use a technology to find our coefficients M and B. And I have a video that shows how to use StepCrunch to find those coefficients. Please refer to that video. And for question C, we're going to use the regression line to predict the expected mileage as of April 25th, 2005, of the minivan made in 1999. So after we put the data into StepCrunch, this is what we got. So this is our scatter plot. You see the blue dots, those are our data values. Does it look like they line up along the line? Well, kind of. So our StepCrunch found the intercept of 19,680 and the slope of negative 9.807, So we can see the negative correlation here, right? As the year of the, as the age of the car increases, the mileage, the year in which the car was made increases, then the mileage decreases. All right, so what is the correlation coefficient, by the way? In StepCrunch, the correlation coefficient is denoted by capital R. In a lot of sources, it's actually a lowercase r. And we see the correlation coefficient there is negative 0.84895, which is a decent correlation, but not a perfect correlation, as our graph shows. So let's write down the our model, our regression line. All right, so notice that when we are writing our regression line, we use Y with a hat here. That represents our model, okay? Our intercept was 19,680, and I'm gonna round to a whole number, the nearest whole number. Minus the slope is negative. We have a negative correlation here. The slope is negative 9.8. Okay, I'm going to use a 10th here. And then what do we take in? What's our X variable? X variable is the year. Make the year in which the car was made. All right, so this is our regression line. And I believe one of the questions was to find the predicted mileage for the car that was made in year 1999. So let's do that. We're going to set X equals 1999. We're going to put into our model. So 19,680 minus 9.8 multiplied by 199. 1999. And so what did I get for the mileage? Expected mileage is 89.8. Remember, it's in thousands of miles. Okay, so that's the predicted value when we use the line. Okay, now what about our actual data value? So in my data set, I actually had a car that was made in 1999. And what was its mileage? Its mileage was 71. So a little bit less than what I got predicted. Now, so if we look at our chart, 1999 is right here. So I have a slight difference between my predicted value and the actual value right here. So that distance between the actual data value and the predicted value is called a residual. And we're gonna talk about what that means in the next video. Actually, I decided to continue in this video because these they're very connected. Everything that we're going to be talking about next is connected to what we're doing right now. So don't want to break it up. So anyway, these residuals are found by subtracting the predicted value from the actual value. And you can see, like, for example, for 2000, we're going to have 1, 2, 3, 4 residual values. And just a side note, the best fit line or the regression line is constructed in a way to make those residual, to minimize the residual, to make them the least. And that's why sometimes this line is called the least squares line, because it takes the squares of the residuals and finds the line that minimizes those squares of the residuals. Okay. So there, basically the software has an algorithm so that selects the line that minimizes the residuals. All right, so definition. The residual for any data point is the difference between the actual value of the data point and the predicted value of the same data point. Okay, so we already talked about it. Let's talk about coefficient of determination. R squared, lowercase r squared, or in StatCrunch, it's actually an upper R squared. Is the percentage of variance in the variable that is accounted for or explained by the variance in the other variable. So, for example, here in our regression line, X was the age of the car or the year made, and not the age, it's the year made. And Y variable was the mileage. So the R squared, it's actually that same R that we use. It's the same correlation coefficient, but it's squared. It's the percentage of the mileage increase that is explained by the age of the car. Okay, so in this case, there is a 72% of the mileage is explained by the age, due to age. The rest of it could be due to different other factors, other variables. such as what I can think about right now, maybe where this car is from, which region is it from, let's say Los Angeles versus San Diego, or some other city. So that could be another variable in play here. Of course, we know some people drive more, some people drive less. So that's another variable, but 72% of it is due to the actual age. So the answer to this question, what percentage of car mileage can be explained by the age, is 72%. And question A, what is the residual value? So the residual for the car made in 1999 was 89.8 is what we found, minus the original value from the data set, which was, I think it was 71. And that could, that's going to be 18.8. I'm going to stop here for this video because it's already getting long, and please proceed to the next one.